Professor Anne, maybe we'll just take a couple of few more minutes. Sorry for the delay. It's just a technical issue that we're trying to get fixed soon. Thank you so much for your patience.
Okay.
Start. Listen. So let me begin by, apologizing to all of you for the delay in the start of the talk due to technical reasons. Well, it's a great honor for me to introduce Professor Anne Lullier, Physics Nobel Laureate of 2023. Professor Lullier obtained her doctoral degree in physics in 1986 from Pierre and Marie Curie University and the French Alternative Energies and Atomic Energy Commission, CEA. She carried out her postdoctoral research at the Chalmers Institute of Technology in Gothenburg, Sweden in 1986, and the University of Southern California in 1988. She served as a visiting scientist at the Lawrence Livermore National Laboratory in 1993. Then she joined Lund University as an associate professor in 1995 and was appointed a professor in 1997. She received the Wolf Prize in 2022 and the Nobel Prize in Physics in 2023, along with Professor Pierre Agostini and Professor Ferenc Krauss, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. Professor Lhuillier discovered a new effect from the interaction of laser light with atoms in a noble gas in 1987. Professor Agostini and Professor Krauss demonstrated that this effect can be used to create shorter pulses of light than were previously possible. These pulses, known as attosecond pulses, can provide images of very fast electronic processes in atoms, molecules, and condensed matter systems. I now request Professor Lhuillier to give a talk.
Thank you very much for this introduction. I'm very happy to be with you, even remotely. So, is everything okay? Can you hear me and can you see my screen?
Oh. Oh, sorry. Oh, yes, we can hear you.
Yeah, we can hear you and see this screen. Thank you.
Okay, so this talk is about attosecond light pulses and application of these pulses. So I think this talk is in the framework of the International Year of Quantum. So I thought I would make a small connection with one of the fathers of quantum mechanics, Werner Heisenberg. And this is a citation from him from 1925, which is the year that we celebrate this year, 100 years. And this is the citation, the formal rules which are used in quantum theory for calculating observable quantities may be seriously criticized on the grounds that they contain as basic element relationship between quantities that are apparently unobservable in principle. And so the question I'm asking is, can we observe the quantum world? And we know that we can measure the wave function square, but can we measure wave function and even the temporal evolution of a wave function? And what I hope to show you is that with these techniques, we can actually measure the wave function of an electron and its time evolution. So and even towards the end of the talk, the density matrix. So this is the outline of this talk. First, I will talk about attosecond light pulses. And so this will be a presentation of what led to this Nobel Prize in 2023, Nobel Prize which I share with Pierre Agostini and Ferenc Krauss. And then I will talk about the application of these techniques to looking at photoionization in the time domain. So this field of research started really from very fundamental studies of atoms in strong laser fields. And multiphoton processes. Here you have a two-photon excitation process, something which was predicted theoretically by Maria Goeppert-Mayer in 1931, could be observed thanks to the invention of the laser in 1960. In the 60s, Russian scientists studied ionization by multiphoton absorption, as you have in this picture. where an atom is ionized by absorbing 4 photons. In 1979, my colleague Pierre Agostini and co-workers observed for the first time above threshold ionization, where an atom can absorb more photons than what is needed for the ionization. And my thesis work at the beginning of the 80s was to look at multiple ionization processes by multiphoton absorption. Here you have, for example, the double ionization of xenon atoms by absorbing many photons. The next step in this research was to look at possible emission from excited atoms or excited ions in this interaction between atoms and a strong laser field. So we set up an experiment where we look at light emitted by a gas of atoms exposed to an intense laser field. And here we use a grating to analyze the radiation, and we have a photon detector. And at that time, I was a young researcher at the Commissariat à l'énergie atomique et aux énergies alternatives in Saclay, France. We did not see fluorescence, but we saw a high-order harmonic generation. Here you have a spectrum observed in argon gas exposed to an intense laser field. And what you see are peaks, the frequency of which corresponds to a multiple of the laser frequencies. So we see, for example, the 13th harmonic up to the 31st harmonic. And this was really unexpected and very interesting at the time. If we plot the distribution of these harmonics as a function of order, we see that for the first order, the intensity decreases, but then there is a plateau where all the harmonics have approximately the same intensity, and then there is a cutoff. And this plateau behavior was probably the most interesting aspect of this result, because at the time we were thinking very much in terms of perturbation theory between the atom and the light, where you can write the polarization induced in the medium by light as an expansion, series expansion in powers of the electric field of the laser. And for such an expansion to be valid, you expect the first order to be much larger than the third, much larger than the fifth, etc. This was obviously not the case because of this plateau behavior. So non-perturbative behavior of the interaction between light and matter. You can also notice that we only have odd order harmonics. This is due to the symmetry of the interaction. Almost immediately was raised the possibility that this light, this high order harmonics, could lead to the production of very, very short pulses of light in the attosecond range. And let me explain the idea. Here I am showing 3 harmonics, so 3 waves, slightly different frequencies. So harmonics 17, 19, 21. If we assume that these harmonics are phase locked, which means the maxima of a wave are at the same time, and this is repeated every half laser period. After one half laser period, the minima are at the same time, and again the maxima, etc. This is what is called phase locking of these harmonics. So if this is the case, if you just sum up these harmonics, you get sorry. You get a train of attosecond pulses, very short pulses, through constructive interferences and destructive interferences, again, constructive interferences, etc. If you plot the intensity of these pulses, you obtain this train of very short light pulses in the attosecond range. The laser which we are mostly using is a titanium sapphire, and the half-liter period of that laser is 1.3 femtosecond. So you see that the duration of these short pulses is of the order of a few hundred attoseconds. If you have not only 3 harmonics, but 10 harmonics, and if they are all phase locked, you can obtain even shorter light pulses. The reason why we get these very short pulses is, first of all, that the frequency of the radiation that we are looking at is in the extreme ultraviolet. It's a high frequency, and this means that the period is short. The second reason is that we have a broad bandwidth, which is due to this plateau. So these harmonics together correspond to a very broad bandwidth. But the question is, are these harmonics phase locked? And it's going to take us about 14 years to really show that, yes, they are phase locked. Yes, we have attosecond pulses. In 1992, there was huge progress in laser technology with the discovery of the chirp-pulse amplification technique that led to a Nobel Prize to the inventors, Gérard Mourou and Donna Strickland in 2018. The new laser material, titanium sapphire, and also a new way to generate femtosecond laser pulses called Care lens mode locking. And here is a picture of 3 Swedish scientists that decided to put these 3 inventions together and to build the first terawatt laser system in Europe based on this new technology. And this was the reason for me moving to Lund in the first place. Here is a picture of myself and my first PhD student in 1991. And we are building a dedicated instrumentation to study high order harmonic generation. And here is a picture of this instrument. It gives you the scale of the physics that we are doing. You don't see the laser, it's behind a hole in the wall. What is inside this instrument is first a gas jet, which you see here. Then some optics, which you have in this vacuum chamber. This radiation is strongly absorbed by matter, so we need to work in vacuum. And then we have a photon detector, which in this case is an electron multiplier, which is here. So at that time in Saclay in France, we were working with a neodymium glass laser system, 1 picosecond pulse duration, very low repetition rate, 1 shot per minute. And we were invited to go to Sweden to work with this new laser system with much better parameters, 200 femtosecond pulse duration, and also a repetition rate of 10 Hertz, so 10 shots per second. And this allowed us to do nice experiments. Here I'm showing one of these results. This was in 1993. Here you have a spectrum obtained in helium atoms showing really high order harmonics up to the 93rd order, and also a very nice plateau behavior. So in 93 was also a breakthrough in the theoretical understanding of higher order harmonic generation and generation of attosecond pulses. To understand this strong laser atom interaction, you need to solve the Schrödinger equation, as is shown here, time-dependent Schrödinger equation with, in this second member, the atomic potential and the laser atom interaction, which is time-dependent. You can treat the electric field as classical and use the dipole approximation. But the difficulty is that this laser atom interaction is comparable in strength to the atomic potential. And the first attempts to solve this problem was to solve numerically this equation. But then in 93 was suggested a very simple and intuitive model called the three-step model, which allows us to really understand what is happening. And this model is illustrated on this cartoon. You have an atomic potential which is strongly deformed by this laser atom interaction, as you see here at some time, making it possible for an electron in the ground state to tunnel through the barrier. Then the electron is outside the atomic potential and is driven by the laser field. The laser field changes of sign. The electron is driven back towards the atom. And then there is a certain probability for recombination back to the ground state. And in this recombination, you have emission of light with high photon energy. So if we look a little more at what is happening, so you have this tunnel ionization and the electron trajectory in the continuum. Electron trajectories that start at slightly different times and come back at slightly different time, and the energy carrying certain different kinetic energies. So in the time domain, you have an emission of so you create an electron wave packet, which after recombination lead to the emission of light of short duration at an attosecond pulse. And the corresponding spectrum is broadband. It's given by the distribution of kinetic energy of the electron when it returns. And you have here this plateau behavior that is due to the fact that the probability to have these different trajectories is roughly the same, and that in the time domain you have very short pulse. So in the frequency domain, you have a broadband emission. Now this process is repeated on the other side of the atom after half of the laser period, and leading to emission of a new attosecond pulse. And now if I add these two attosecond pulses and go in the frequency domain, I get a modulation of this broadband spectrum, and we see the apparition of peaks separated by twice the laser frequency, and this corresponds to this periodicity of half the laser period here, periodicity which is accompanied by the change of sign of attosecond pulses from one to the next. And then this process is repeated again and again, and you have interferences of all these attosecond pulse leading in the frequency domain to a frequency comb of high order harmonics with odd order. This is very similar to diffraction through multiple slits in the spatial domain, leading to interference in the far field. Here we don't have slits in the spatial domain. We have slits in the temporal domain, leading through a Fourier transform to the spectrum of high order harmonics. Now, the physics of this phenomena would not be complete without also including the response of a macroscopic medium. In order to have harmonic generation, you need that the emission from all of the atoms in the medium to be phase matched, to be in phase, as is shown in this cartoon. This is called phase matching. This is described by Maxwell's equations, which can be simplified to a wave equation, as you can see here, with where you have here generated field due to the polarization induced in the medium. And for this phenomena to be efficient, you need that the phase of the generated field to be equal to the phase velocity of the generated field to be equal to the phase velocity of the polarization induced in the medium. And this is described by this equation here, where I write the phase mismatch between the generated field and the induced polarization. This should be equal to 0. This is very similar to what you have when you look at nonlinear optical processes in a crystal, for example. So you need this delta K to be equal to 0. K is the wave vector. In this problem, the delta K depends on the dispersion of neutral medium, the added dispersion due to the presence of free electrons in the medium due to partial ionization. And you also have an influence of the focusing of the laser as well as the electron trajectory, leading to an accumulated phase along the trajectory. So I want to summarize the whole subject in itself. In order to achieve phase matching, it's important to have a partial ionization of the medium, but not too much, typically as a few percent. Phase matching can be achieved in a variety of conditions. It's very flexible. The reason is that this phase mismatches that you see here depends on several parameters, so you can adjust them. So phase matching can be realized in high pressure gas jets, in capillaries, also in low pressure cells. However, the conversion efficiency remains low. It's of the order of 10 to minus 5 at best. This is mainly due to the single atom response of the atom, the emission of attosecond pulse. The probability for this phenomena remains very low. 2001 was really a breakthrough in this field because it was really the first measurement of attosecond pulses. This was realized by Pierre Agostini and Ferenc Krauss. Pierre Agostini managed to measure attosecond pulses in a train of pulses using a technique called Rabbit, which I'm going to present in a moment, while Ferenc Krauss managed to generate a single attosecond pulse and measure it using a technique called streaking. Both techniques are cross-correlation methods based on laser-assisted photoionization of a gas and photoelectrons detection. So I'm going to explain in a moment that the technique used by Pierre Agostini, the technique used by Ferenc Krauss is actually quite similar. So now I'm going to go to the second part of this talk, which is really application. And I'm going to focus on a very simple process, which is photoionization. When an atom, or it could be a molecule or condensed matter, Well, so when an atom absorbs a photon and is ionized and leading to the emission of an electron. And the kinetic energy of the electron is given by this formula where h nu is the frequency of the light and IP is the ionization potential of the atom. And this is the photoelectric effect, which was discovered by Hertz in 1887 and explained by Einstein in 1905. And to explain this formula here, Einstein had to use the new concept of light quantum, which was previously introduced by Max Planck in 1901. And again, this was really the beginning of the quantum mechanics. But in this talk, I'm not going to focus on the frequency of light, on the light properties, but really on the photoelectron. What are the properties of this photoelectron? Maybe you think of it as a particle with a certain energy or a momentum, but we know that it is also a wave. So can we measure the wave property of the photoelectron, the phase of this photoelectron, or a little bit more generally, the quantum properties of the photoelectron? So how do we do that? What is the experimental method? Well, if you ionize a gas, ionize an atom with a train of attosecond pulses in the frequency domain, this high order harmonic come, you will not get any information on the temporal domain. You ionize with the harmonics and you get peaks, electron peaks with a certain kinetic energy given by the formula of the photoelectric effect. And these peaks are separated by twice the laser frequency because we only have odd harmonics. In order to have temporal information, you need to have also a probe field. And what we use is the fraction of the laser, which is used to generate the high harmonics. So with frequency omega. In the time domain, this is your optical wave. And this probe field is used to induce two photon processes where you have absorption of one harmonic plus a laser photon or the next harmonic and then stimulated emission of a laser photon. So you create side bands and these side bands can be obtained by two processes, by absorption of a harmonic plus a laser photon or the next harmonic and emission of a photon. So you have two quantum paths leading to the same final states. So you have a quantum interferometer. And this interferometer is going to give you information on the phase of these two ionization processes because we add amplitudes. This is quantum mechanics. Now, if you want to have to observe interferences, you need to vary something in this interferometer. And what we vary here is the time delay between this probe field and our train of attosecond pulses. And this technique is the technique used by Pierre Agostini and co-workers in 2001 called RABBIT, like reconstruction of attosecond beating by interference of two photon transition, based on a theoretical idea in the group of Alfred Mackay. Now, how do we do that in practice? First, we need an optical interferometer, as you see here, looking like a Mach-Zehnder interferometer. In one arm, we generate harmonics and we get rid of the fundamental field. So we have attosecond pulse train. And then we have a probe arm where we have a delay stage, and this interferometer needs to be extremely well stabilized. We need to have a very stable interferometer on the attosecond time scale, like 1020 attosecond. And then we have a recombination mirror here. So this is what we get, this combination of attosecond pulse train and a probe field, and we can vary the delay between the two. Then we focus this light by a toroidal mirror into a chamber where we ionize the gas, and we collect the electrons. We do electron spectroscopy. In the results I will show, we use magnetic bottle electron spectrometer. This is an example of a rabbit scan. This is the name. Electron spectrum as a function of delay. And what you have is a series of peaks corresponding to this 1 or 2 photon absorption processes that I have presented to you. And you have the main bands and side bands. And then you see oscillations of the side bands. And the period of the oscillation is half a laser period, which is 1.3 femtosecond. If we represent what we do using a clock, we measure small time variations. So it's always nice to talk with the help of a clock. So in this type of measurement, 1 hour of a clock is 1.3 femtosecond, 1,300 attosecond. And what we can measure is the position of the sideband oscillations very accurately. We don't know actually where the position of the sideband is. We do not have any absolute delay measurement, but we can measure very accurately the variation of the delay between different sidebands. So we can measure the variation of this arrow very accurately. So what it is that we are doing in this measurement, we are characterizing a wave packet, which is here shown in blue, due to excitation of absorption of an atom by several harmonics or by attosecond pulses in a train. And we characterize this wave packet by this interferometric technique, using sidebands and measuring the oscillations. So what we measure is really the variation of the phase offset of this oscillation, which we can write as a delay. And what is this? The interpretation of this delay. This delay actually depends both on the excitation pulse. This represents the group delay of the attosecond pulse, and this is why this technique was used in the first place to characterize the attosecond pulses in a train. But it also carries information about the group delay of the photoelectron, which is created in this interaction. So you have really two quantities here. Let me give you a physical interpretation of this group delay. It's represented here. This is really the group delay of the electron wave packet, which is created by absorption of light as it propagates out of the potential. And it's very similar to group delay of a light pulse going through a material. Here is the group delay of the electron wave packet as it propagates out of the potential. And it's related to a well-known quantity in the theory of collision called the scattering phase, which was introduced by Wigner already in 1955. So what this group delay is the derivative of this scattering phase. Why half? Because it's only half a collision process. It's a photoionization process. So how can we distinguish between what is due to the excitation pulse and what is due to the photoelectron? Well, we can calibrate. I would say in most of the case, this second term is much smaller than this one. So this is what we measure. And then we can use, we can measure differences of group delays, or we can calibrate with a well-known measurement. I will show you that in a moment. So let's consider photoionization of xenon atoms in the 4D shell. And again, what we would like to do is really look at the dynamics of this ionization process. So xenon, the outer shell is n equal 5, and so 4D is the first inner shell, valence shell. So how do we have access to the dynamic of this ionization process? Here we have an old result obtained a long time ago using spectral lamps and showing the cross-section for ionization in the 4D shell. And you see a very nice resonance phenomenon. It's called a giant dipole resonance, particularly by Göran Vendin, who interpreted this resonance in terms of a collective effect of the 4D electrons. But now we don't want to have only this spectral information. We also want to have time information. So how we go from frequency to time. But to be able to go from frequency to time, we also need phase information. Phase information, or we don't care about an absolute phase, but what is the variation of the phase, derivative of the phase, or group delay. And this is exactly what our technique allows us to determine, is this group delay of the photoelectron. And here is the result. This is for 4D 3/2 electron. We need to include relativistic effects in this, in the case of 4D ionization of xenon. And this is the measurement of the time delay. So how do we know that what is measured is the time delay, this Wigner delay, and is not influenced by the excitation pulse? Well, we measure simultaneously ionization of neon atom in the 2p shell. And in this case, we know that the group delay due to ionization is negligible. So it's only due to the excitation pulse. So we can simply subtract the effect of the excitation pulse. And what we show here is this time delay due to the photoionization process. So what do we have in this result? We have the effect of the giant dipole resonance that leads to delays of a few tenths of attosecond. It's a broad resonance, which is peaking at 100 eV. So you can imagine something like this. And then there is something happening at threshold, leading to much longer time delays, which is due to, we think, to a spin flip and a spin orbit interaction. And we can now really interpret the photoionization process using an effective type of potential. And in the case of for energies in this region of the giant dipole resonance, we have a very small trapping of the photoelectron, but the lifetime of the photoelectron is kind of short, while in at low photon energy, the electron is really much more trapped in the potential and leading to long delays. Let me give you another example, which is resonant ionization of helium atom. Close to so the 2s2p state. So it's a beautiful example of a quantum interference effect. where an atom of helium can be ionized either directly or by first excitation to this excited state, followed by autoionization. Now what we can do with our technique is not only measure the amplitude for this ionization process, the intensity, the cross-section, but also the phase using this interferometric technique that I shown you before, projecting to a sideband and then varying the delay and measuring the interference pattern. And these are results where you have here the amplitude of the process, which show a very nice interference pattern, while the phase shows a high phase variation. And since we have the amplitude and the phase, we can, as a function of photon energy, we can now go in the time domain. So we can go a Fourier transform and extract the dynamics. We can even do better than that. We can do a time frequency representation. And this is what is shown here. This is a Wigner distribution of the photoelectron distribution. And this plot show kind of show you how the ionization is taking place in time, starting with feature here, which can be attributed to direct photoionization, broadband feature, broadband in frequency and short in time. And then you have a strong interference pattern when these two arms are comparable in strengths. And finally, at longer times, you have only this excitation process followed by autoionization, narrower in energy and longer in time. To conclude this talk, I would like to tell you about recent results where we try to do a deeper characterization of the photoelectron, trying to really measure the quantum state. And the reason we started to think in these terms is that we thought, but we cannot all the time discuss this photoelectron as a fully coherent wave with a phase and amplitude. Sometimes you have some of incoherent process which make this impossible. So let's, can we do better? Can we really measure the quantum state of a photoelectron? And the technique is a little bit similar, but instead of using just a probe, now we use two frequency components. We have a bichromatic probe. So let's look at the excitation process. So it's a similar idea. We create a sideband and we want to get information in how the sideband varies between the delay, between the excitation pulse and this bichromatic probe field. So just to show you better what we are after, I'm kind of splitting this XUV photon into two, but in the same bandwidth. So you see here that we can reach a final state in this sideband peak by two quantum paths using different components of this bichromatic probe field and going through different continuum states of this photoelectron wave packet. So same idea, we have a quantum interferometer here and we get a signal here which oscillates. The frequency of the oscillation is not 2 omega as before, but now delta omega, which is the frequency difference between the two components. And now the contrast of this oscillation is going to depend on whether we have a well-defined phase relationship between these two continuum states. On the other hand, it will which means that it will depend on the coherences of the density matrix, and the phase of the oscillation will be related to the phase of the density matrix. I put a little e here, which means that it's the density matrix of the photoelectron. So this technique is a quantum state tomography of an attosecond electron wave packet. We gave an acronym which is Kraken, which is based on Swedish language. How do we do this bichromatic probe here? A little bit of optics. What we do is we sculpt actually a part of the spectrum of the incident laser using an instrument called 4F shaper, and which used two gratings in a 4F configuration. And in the focus here, we put a slit which allows us to select two frequency components. And these are oscillations which we observe for different pairs of this bichromatic probe. And from these measurements, we can extract the subdiagonal of a density matrix. So what we have here is the density matrix of a photoelectron. So energy, and the diagonal is this one. From this measurement, we can make a fit using a Bayesian optimization procedure, and this is the result obtained in helium. It's not very interesting, you may say. It's a round density matrix, which is characteristic of a pure state, and we don't expect anything else in this case. It's non-resonant ionization. It's a simple process, coherent. And we can measure the purity of this density matrix, and we obtain something very close to 1. Now, what is interesting is when you do the same measurement in argon, then you obtain a density matrix which is not round anymore. It's oval, which means we lose coherences in this region here. And this is characteristic of a mixed state. So why do we create a mixed state in argon? It's because of the spin-orbit interaction. When we ionize argon, the ion can be left into the P1 half state or P3 half state. So we have actually two distribution of electrons. So this photoionization actually leads to an entangled state between the ion and electron. If we create the ion and in the 1/2 state, then the electron will be in the 1/2 state, and similarly for the 3/2 state. So we have an entanglement, and since we only measure the reduced density matrix, we lose information, and this explains that we obtain this density matrix with a purity equal to 0.65. The smallest purity that you can get in case the photoelectron distribution are completely separated is theoretically 0.55. We don't obtain this because there is a slight overlap of the distribution. So if a photoelectron is born with this kinetic energy, then you don't know what is the state of the ion. And this is why it's a little bit higher purity. So you see that we can even adjust the entanglement by adjusting the bandwidths of the XUV pulse. So I'm coming to the end of this talk. Attosecond science is a very dynamical field at the moment. There is a lot of things happening. There are applications in many fields. I presented what we're doing in atoms, but of course there are application in molecules. This is called attosecond chemistry, in condensed matter, and also more applied application in the industry, and also this very exciting field which I presented at the end, which I'm calling ultra-fast quantum dynamics, looking at quantum phenomena in very fundamental quantum processes in different way. There are also a new source of attosecond pulses the last 2 or 3 years via free electron lasers. And this is very interesting because these pulses are very complementary from attosecond pulses created by high order harmonic generation. They are in the X-ray higher energy per pulse. And they exist now at the LCLS in the United States, and also at the European XFEL, and you have also a very interesting experiment at Fermi in Italy, and there will be more and more. With that, I would like to thank you for your attention. I would like to also thank my group of research that you see here with the senior people indicated here. This research, of course, needs some organization financing it, and for me, it's the European Research Council, the Swedish Research Council, and also the Wallenberg Foundation. And I would like to again thank you for your attention and for inviting me to give this talk. Thank you.
No. So I mean, thank you very much, Professor, for this very insightful talk. So I think if there are any questions, are there online? Any question? No. Okay. So any questions by anyone in audience? So is there any time limit on how short a pulse can be? Is there some fundamental limit?
There's no fundamental limit. And I know there is some research on getting shorter and shorter pulses. The record at the moment is 43 attosecond. The difficulty is to make all of this light to be phase locked. So it's easy to have many frequencies over a very, very broad range, several hundred an EV, but to make all the frequency component to be in phase, it's more difficult. So it's not fundamental. I would like to say it's technological limit.
So I mean, what do you see in future? I mean, how can we progress further to have an even shorter duration pulses?
I don't know actually. I think you can again, it's a technological limit more than anything else. You need to do you need to have filters. You need to compensate for the chirp that if I think in using high order harmonic generation, the harmonics have a slight chirp between so that or the attosecond pulse have a chirp. You need to compensate for this chirp. So you need to go through material. I think I would like to say that most of the community is not doing these kind of things because we are trying to use these pulses for application more than trying to get even shorter pulse. But I would like to say this is not too difficult to do that experimentally. So I think there is a lot to do.
I think we have a question online. What is the symmetry due to which we only observe odd harmonics?
The symmetry is the symmetry relative to the symmetry relative to the origin, the inversion symmetry, if you want, and you can if I go back to Yeah, you actually see it here. It's you have this symmetry. This is the position of the atom here in the middle. So it's a symmetry. It's the same process here and here, but inverted. So there is the inversion symmetry, and this kills the order harmonics. You can also see that there is a sign flip between consecutive attosecond pulse, killing the even harmonics. If you break the symmetry between consecutive consecutive pulses, which can be done using a second color, for example, then you will recover the even harmonics.
Thank you, sir. Any other questions anybody wishes to ask? Yes. Sir.
Thank you, Professor. This is a very interesting talk. I have one question regarding the same spectrum that you have shown in the beginning. So I have seen that the odd harmonics are present, but the intensity fluctuates. What is the reason of this fluctuation of this intensity of those peaks?
I think I can go back here. Yeah, so here, this is what you mean, this spectrum.
Yes, yes.
Yeah, I think this was really the first measurement, and I think it is much better. And what I showed afterwards, here you see that it's already much better. So I think between consecutive peaks, it's quite it is really a plateau.
Okay, okay. Thank you.
Hello, doctor. May I ask a question if this is fair?
Yes,
My question is, you mentioned that a conversion efficiency of 10 to the minus 5 with a driving laser intensity of the order of 10 to the 13 watt per centimeter square or so. Could you clarify what intensity the generated harmonics correspond to in watt per centimeter square unit?
The intensity that you need to generate harmonics is of the order of 10 to 14 watts per square centimeter.
Okay.
And it can. The point is that, of course, now we can use much higher intensities, but it doesn't help, because if you have too high intensity, then you have a lot of ionization in the medium and you destroy phase matching. So there is a really window of intensity where this works. You need high intensity to have this intense light matter interaction, but not too high, because then you destroy phase matching. And this is also the reason why it's very difficult to get higher conversion efficiency. We're trying by all possible ways, but we are limited by the intrinsic phenomenon.
Okay, thank you. Ma'am, I have another question regarding the rabbit scan. So the side bands, they have they are showing peaks with respect to delays.
Yeah.
Yeah. Yeah. Yes. Yes. So the peaks in the side bands, uh, I, I think they are not aligned. I mean, horizontally. I mean, one is shifted upward, and the righter ones are kind of shifted downwards. So can you give any insight that why this is happening?
Yeah, this is a very good point. No, they are not exactly aligned, as you can see here. And this is due to actually to this attosecond chirp, the fact that there is a the the electron do not come back exactly at the same time. So I can also show you this. Now I'm going back to this. So you see here on this, this is really a cartoon, but it says that the electron here coming with a low energy come back a little bit before those with a high energy. So you have a certain chirp, and this is what we can measure with the rabbit technique. So these attosecond pulses are not at all transform limited. They have a they have a certain duration, which is due to this what you can see here. This the fact that the electron with different kinetic energy do not come back exactly at the same time.
It's clear, ma'am. Yes. Thank you so much.
Well, I just have a question on attosecond entangled, quantum entangled photons. I presume they can be used for fast quantum communication. What do you think?
I really don't know. So what I showed was really entangled electrons, but not entangled photons. But there are a lot of research at the moment to on this. What is the field of high order? This corresponding what are the property of the light of these harmonics, and in some case there is a prediction that we have really completely entangled photons, at least in some cases. So this is a beginning field, and I cannot really say whether there should be application in quantum communication. Would be very interesting, but it's kind of beginning field so far. Quantum and ultrafast has been kind of a little bit different field of research, but at the moment there is really at least part of the community is really working on this aspect, both on the photons and on the electrons.
Thank you.
Anybody else? Yeah, okay, I mean, Professor, do you have any advice? So we have many students here in the audience who have joined PhD program in last 1 year. Do you have any advice to these students? I mean, how can they have a very fruitful and enjoyable scientific research career?
Yeah, it's a difficult question. Well, if you are already a PhD student, that means you you have already chosen your field of research. I think if you should try to continue in academia if you like it, and if you like teaching, and if you like research. Probably you need to be very obstinate and to accept that sometimes it's very tough, and you have ups and downs, especially coming from India. You need to probably to travel a little bit and then find positions. So one needs to be very yeah, very dedicated. But at the same time, it's a fantastic career. So I would encourage to do that, but remember to have a life as well. Yes.
Okay. So anything else anybody wishes to ask?
So may I ask a question?
Sure, go ahead.
Is the harmonic emission from a single atom, are they phase locked naturally?
Almost. You have this chirp I was mentioning. So if I go back to this picture here, this one, this is kind of cartoon to explain the idea. But what happens is that this straight line here in orange, they are a little bit like this. They are tilted because of this chirp. But it's not too bad. You still have a constructive interferences leading to 2 short pulses.
Okay, thank you.
Very, very good question.
Yeah, thank you.
Is there any other question? Okay, there is no other question. Okay, so I think we should thank our speaker, for a very educative and informative talk. And we thank you for taking time from your very busy schedule to address this audience. So thank you very much.
Well, thank you, all of you, and good luck.
Thank you.
And bye-bye.
Thank you. Thank you.